Hello everyone, and welcome back to this Nanophotonics and Plasmonics course. Now that we know about localized surface plasmons, what they are, where they came from, as well as how we can calculate them, it is now important to look at the properties of those elementary excitations. So the first thing to notice is that the plasmon energy depends on the shape of your object. So we've already seen in the previous chapter about the bulk plasmon that has a frequency omega p, which is given by this expression. We also covered the surface plasmons that are with a frequency omega p over square root of 2. The frequency of plasmons for a sphere, which are given by omega sub L, where L is an integer, and this is the expression. You can calculate the frequency of a dipolar resonance where L equal 1, a quadrupolar resonance where L equal 2, and so on and so forth. Now, if you look at another case, for instance, the case of a cavity, which is a complementary geometry to a sphere. So where your sphere, you have a metallic sphere and the surrounding dielectric. Here we have a dielectric sphere and a metallic surrounding. In this particular case, you still have a metal dielectric interface. And basically this cavity, this spherical cavity, is going to sustain localized surface plasmon modes, which frequency is going to be given by this expression. So you see that it's very similar to the sphere because of the symmetry, but now you have this L plus 1 rather than this L. So the plasmon modes of a spherical cavity for a given size is going to be slightly higher than the plasmon mode of the sphere of a similar size. Another concept, which is the plasmon hybridization. So similar to atomic states in atomic physics that hybridize to form chemical bonds via bonding and anti-bonding molecular orbitals, plasmon modes also hybridize to form some form of bonding and anti-bonding combinations of hybridized plasmon modes. So this plasmon hybridization theory, which was developed by Peter Norlander at Rice University in 2003, is extremely powerful because it really gives an idea about how to engineer the plasmon resonance to construct optical properties you want. So very similar to how you form molecules from atoms. Then you can form also hybrid plasmonic states from the hybridization of more primitive structures. So if you take, for instance, a gold nanoshell with a dielectric core, this is the result of the hybridization of a gold sphere and a cavity. If you take a sphere, you have a bunch of modes, which frequency are given by the expression we've seen before. So in the case of a dipole, the frequency of the dipole resonance of a sphere is omega p over square root of 3. In the case of a spherical cavity, is omega p square root of 2 over 3. A dipole of a sphere, a dipole of a cavity, and they're going to form bonding and anti-bonding, or symmetric and anti-symmetric hybridized modes. So basically you're having the negative and the positive charge distribution of a sphere, and then you have the positive and negative charge distribution of the cavity, and you can actually flip the signs of one or the other to get these symmetric and anti-symmetric combinations. These are the frequencies of the symmetric and anti-symmetric or bonding and anti-bonding dipole of the nanoshell. So something to notice is that you have the aspect ratio of your geometry in that particular case. This X is connected to the thickness of the shell. So when you change the thickness of the shell, you're gonna change the energy of your dipole resonance. So the plasmon hybridization is very powerful because it actually allows to engineer and understand how the modes evolve as you change the geometries. So in the case of a nanoshell, as we've seen, when you change the thickness of your shell, even if you maintain the overall size the same, then you'll be able to actually change the energy levels of your hybridized states. Plasmon hybridization also applies to a variety of geometries and structures. In interactions, you have two spherical nanoparticles that are brought closer together. The light, incoming light, which is polarized along the long axis of the dimer, you're going to have two induced dipoles that they're going to be interacting. So you can have them in bonding and anti-bonding configurations. Now, if you excite the particles on the transverse direction, you're going to have the dipoles that are now aligned in these orthogonal directions, and you're going to form two of the bonding and anti-bonding dipoles. In the case, for instance, of a dimer of nanorods, you can have this transverse dipole for the nanorod, or the longitudinal dipole, and then they can interact to form a variety of different modes depending on how you actually place the two nanorods with respect to each other. If you're basically aligned, if you're parallel, or if you're forming more complex configurations, and depending on how you're going to excite the system with light. So the Plasmon hybridization is very powerful. So this is only for dipoles, but of course this is more general, and this can be extended to other modes like quadrupoles and other modes, although the interpretation would be more difficult. If you take the case of a dimer, you can also look at how those modes evolve when you actually change a given geometry. If you have two nanoparticles that are with a certain separation distance, then you can calculate the energy of this bonding and anti-bonding mode. So if they are very far apart, you basically have two isolated nanoparticles. Each of them is going to have a dipole, L equal 1. You're going to have a quadrupole, L equal 2, an hexapole, L equal 3, and they are at given energy. So this is for very large separations. As you bring the nanoparticles closer together, they're going to start interacting via this Plasmon hybridization. And then the dipole is going to start interacting, forming the bonding and anti-bonding dipole resonances. And you see that they start shifting apart. So you have one that goes to lower energies. The other one goes to higher energies. The same occurs for quadrupoles. So you see that the quadrupoles, they start splitting, and they start interacting a little bit at closer distance, closer range than the dipole counterpart, but they do split as well. So you see that this one, that's a bonding quadrupole that basically goes down in energy, and this one goes up in energy. And you can of course see the same for any type of higher order modes. So the closer the nanoparticle, stronger the interactions, and the stronger the hybridization, the larger the spectral shift. So you can really engineer the optical properties by playing with interactions between nanoparticles. And this is what people have been doing when looking at different type of configurations. You have just a dimer, you have a certain type of optical response, and if you place multiple nanoparticles and start forming longer chains, you see that you start modifying the optical spectrum. So this is the extinction cross section, and you see that now you have more resonances. You start shifting this resonance. You can actually look at how the resonance shift as you increase the number of nanoparticles. You can place them in different configurations, like forming nanoclusters from a single sphere. You have only a dipole resonance. You have dimers where you have bonding and anti-bonding resonances, and then you have trimers and tetrahedra. And you see that you shift the spectrum, you add additional modes, you can change the optical properties by just changing the configuration. These are some examples of nanoparticle oligomers that are meant to mimic hydrocarbon molecules like benzene, so forming those very regular rings with a different number of nanoparticles. So you can really manipulate and engineer the optical properties the way you want based on Plasmon interactions and how you arrange the nanoparticles close to each other. Another way you can actually manipulate also the optical properties of nanoparticles by changing the shape or the aspect ratio of nanoparticles. With this, so this is, for instance, the spectrum of a gold nanoshell showing the bonding and anti-bonding resonances. So you see that as you change the thickness of the shell, you can have a drastic spectral shift of those resonances, and that's basically going to result in a different color of the nanoparticle solution. So you have nanoparticles that are basically now very resonant at below 400 nanometers wavelength or 500 nanometers wavelength. So you can really tune where you want the Plasmon resonance to be by just changing the thickness of the nanoshell. You can do something similar with nanorods or elongated particles in general. If you change the aspect ratio, you can really tune the Plasmon resonance over a large spectral range. So this is the black spectrum, for instance, shows the longitudinal dipole resonance of a gold nanorod with an aspect ratio of 2.4. You elongate the nanorod, then you shift all the way to pretty much 1100 nanometers from 650 here. So it's the same thing. This can be visualized directly from the nanoparticle solution. So the particles will basically absorb and scatter light at different wavelengths. And finally, we discussed about dimers, the plasmon hybridization. So if you just change the separation distance between nanoparticles, you can obtain a very similar way. So going from very isolated nanoparticles, where you have a single dipole resonance, all the way to strongly coupled particles that have a bonding and anti-bonding dipole resonance, and then you can even go to the extreme, and then you have bonding and anti-bonding dipole resonances, and then you start having quadrupole bonding and anti-bonding also that are showing up. So this spectral tunability of the nanoparticles covers a very broad spectrum because you can play with the shape, as we've said, or with the interactions, but you also can play with the composition. So recently, aluminum nanospheres and nanoparticles in general have shown a tremendous interest because they can go down to the UV thanks to their high plasmon energy because they have, if you remember, very large carrier concentrations in the conduction band as opposed to silver and gold. So you see that you can tune the plasmon resonances from fairly low in wavelength or very high frequencies and energies in the UV, all the way to even the mid-infrared when you change the nanoparticle shapes. So this is something which is very valuable for applications because you really can take advantage of the full electromagnetic spectrum from UV to mid-infrared. Another very interesting property of plasmon resonances is that they basically give rise to very strong localization and strong enhancement of the local electric field around the nanoparticle surface. So if you look at, for instance, this example of gold nanostars, where you have very pointy arms, when you excite those nanostars of different sizes with light which is polarized along a given direction, you see they have a very strong local electric field enhancement close to the tips. So you have very localized. So these are just a few nanometers regions where you have very strong localized electric fields that are 100 times or 1,000 times more intense than the incident field. So you're really concentrating the local electric field close to very sharp features. Now, if you have nanoparticles that are organized and interacting between each others, you can really localize the electromagnetic fields in the gap regions between the nanoparticles. So you can really play with the size and shape of those nanoparticles to really confine the local electric fields at the given regions of the structure. So in that case, in the gaps between the nanoparticles. So if you have, for instance, a dimer, you can localize this electromagnetic field in the gap region when you excite the nanoparticle dimer with an electric field which is polarized along the main axis of the dimer, and that's pretty strong field. So you see that you're reaching 250 times larger field in the gap as opposed to the incident electric field. Now, if you basically rotate the polarization of light, if you excite the particle with just the transverse direction, now you have basically a factor 10 lower field enhancement, and you see now the field is localized on the transverse direction. You can really have platforms that are really polarization dependent, and you can control where the field is and how strong the field will be by just changing the polarization and nanoparticle arrangement. So where does this field enhancement come from? If you look at the case of a dimer, if you have two nanoparticles that are fairly isolated, so you see that you have this field enhancement that are basically distributed on either side. So you have these dipole resonances that are forming is because you have a positive and negative charge that are being formed as a result of the plasmon resonance. Now when you bring the nanoparticle closer together because of this Coulomb attraction, you're gonna basically display some of the charges. So you're gonna have more positive charge close to the gap and more negative charge close to the gap because you have those larger charge separation in the gap. You're forming a much larger electric potential, and therefore you're forming a stronger electric field. So, and you go to the extreme, you have very large localized electric field in the gap. Those electric fields can be imaged as well, so you can use near field microscopy, and I strongly encourage you to go back to chapter 3 to look at this near field microscopy. So basically you can image the optical near field of the plasmons, both the amplitude and the phase. This is, for instance, calculation showing the theoretical amplitude and phase of a dipole resonance for a nanodisk. And these are measurements that are done using near field scanning microscopy. And you see that you can recover the two lobes of the nanoparticles, and you can see that the 90-degree phase shift from one side to another, which correspond basically to the charge distribution on either side. So when you bring a tip in close interaction with a nanoparticle, you have these multiple scattering events that can occur. So I encourage you also to go back to chapter 4 on optical interactions to understand about this type of complex interaction between a tip and a plasmonic nanoparticle. These are some of the examples. For instance, a gold nanorod. So you see that you have the measured amplitude and phase. You cut this in two. You have now two nanorods that are interacting. So you see that you have two dipoles interacting, forming a bonding combination. You have a bonding dipole because now you have two nanorods that are interacting. So this can be done using a variety of probes, but typically near-field optical microscopy is done with plasmonic nanoantennas. You can take advantage of this near-field to actually probe molecules and quantum emitters, for instance, so you can really study interactions between the near-field and those quantum emitters. Now I want to emphasize one more aspect of the plasmons. Is their sensitivity to the environment. A nanoparticle which is placed in a homogenic dielectric medium will experience a different optical excitation. The plasmon resonance will shift. This is what we call dielectric screening. So these are some examples, for instance, of plasmon resonances of gold nanorods that are placed in different media, with dielectric permittivities of 2.5 all the way to a dielectric permittivity of 4.5. So you see that the exact same nanorods, when changing the surrounding environment, are going to experience some plasmon resonance shift. So you have a spectral shift. It's a rate shift. This resonance is rate shift when you increase the dielectric permittivity or refractive index of the surrounding environment. So you have this linear dependence on the refractive index, and this is something which is very valuable because it can actually be used for sensing application. So what happens? Typically, if you have a nanoparticle, if you excite this nanoparticle, you're going to generate positive and negative charges. In this case, it's a dipole. And now, because the surrounding medium is not air anymore, but it's a polarizable medium, then you're going to induce automatically charges in this medium. So you're going to polarize the surrounding medium due to the presence of this polarized nanoparticle inside. So because you have positive charges here, you're going to generate negative charges on the other side and vice versa on the bottom. So now because you have these additional charges around, so you're going to reduce the effective net dipole moment of the particle, and then basically you're going to lower the energy of the plasmon resonance. Because you lower the energy, you increase the wavelength, and that's why you observe this spectral shift. And as I said, this is the underlying effect for LSPR sensing that we're going to be discussing in chapter 11. The other thing we can do, instead of placing the particle in a homogeneous dielectric medium, we can place it near dielectric substrate. You can observe spectral shift. So the amount of shift and the direction of the shift will depend, of course, on the incident polarization and depends on the dielectric permittivity of the substrate. So that's also going to allow to actually lift some degeneracy of the LSP modes, because now the dipole resonance along this direction will not have the same energy as the dipole resonance on the horizontal direction. And finally, it's going to also be able to enhance higher order modes. I will not necessarily spend too much time on that, but just to let you know that now, because of this here, we're going to have high order modes. So this is known as the image charge. And why? It's because now, similarly to before, we're going to induce charges in the substrate as a result of the fact that now with this substrate is polarizable medium. This is the image charge, so you can see that you have now an image of this dipole. So if you have the particle excited with this direction perpendicular to the substrate, then you're going to basically have two electric dipoles that are going to be aligned with respect to each other. And basically, if you look at this, it looks like very much like plasma hybridization in a dimer configuration. So you have this effective dimer, basically, that will give rise to bonding and anti-bonding modes. So if you look at this particular case, so this is like 90-degree excitation. So experimentally, in that particular case, they've done 75, but that would be the equivalent of this curve. So you have this very strong bonding mode, bonding dipolar resonance here. Now you can flip the polarization and look at something which is actually transverse or parallel to the surface. Then you're going to have this dipole moment pointing in one direction, and the image going to be pointing in the other direction. And because of that, you're going to reduce the overall net dipole moment. And that gives you basically the black curve here. So you see that you have a different Plasmon resonance now as opposed to the first configuration. So they are both dipoles, but now we see that because of the presence of the substrate, they have at different energies. And of course, you can change continuously the polarization from one to another. So the red one, for instance, is something which is intermediate. And you see that you have now maybe something which is close to 45-degree excitation, where you excite both modes with the same strength. So we can play with the shape of the particles. People have been able to synthesize using bottom-up approaches, so chemical synthesis, a very wide range of geometries and compositions. And this is just a very small sample of what you can find out there, from very simple nanospheres to more complicated nano cages that are basically hollowed cubes or very nice pyramids. You can also play with the shapes using top-down approach, which is basically lithographic techniques, depositions, evaporation. So these are large-scale techniques, typically on substrates, as opposed to the previous one, which are in colloidal solutions. And you can really design very complex arrays, complex geometries, complex patterns. So you have you have a lot of freedom in terms of controlling the geometries, the arrangement of the nanoparticles, the placements, and basically just there's no limit to the creativity of what you can do. Those techniques are more expensive, but you can really control very accurately the size, the shape, and the position of the nanoparticles. So this is just to summarize what we've seen in this chapter. So we introduced the concept of localized surface plasmon. We discussed the general scattering problem and how to solve the scattering problem using Rayleigh theory or quasi-static approximation, introducing the polarizability of the nanoparticle or closest-osmosity relation, introduced the concept of optical cross-sections, and then we moved on to more accurate analytical models like the Mie theory, introducing retardation effect and surface scattering. We discussed also what's beyond Mie theory with electrodynamic methods that we've seen already in chapter 7. And we discussed about the properties of those localized surface plasmons, so plasmon hybridizations, spectral tunability, near-field localization and enhancement, as well as environment effect that are both dielectric screening and image charge.